Most welders develop a habitual torch angle based on what feels comfortable for their wrist, but the direction you lean that torch determines the width, depth, and structural integrity of every joint you touch. Choosing the wrong angle leads to immediate consequences. You'll either blow holes through thin sheet metal or leave a hidden lack of fusion deep inside a thick structural joint. We define these options by torch lean. In the forehand or push technique, the torch tilts forward 5 to 15 degrees, pushing the molten puddle ahead. In the backhand pull technique, it tilts backward 5 to 15 degrees, dragging the puddle behind the arc. This shift in angle is your primary tool for controlling how heat is distributed and how deep the weld fuses into the base metal. A perfectly smooth, shiny weld bead looks great on an inspection report, but a clean surface can mask serious internal failures. Pushing produces a wide, flat bead, but cushions the heat, stopping fusion before the joint's root. Pulling strikes the root directly, resulting in a taller crown and deep penetration. On thick plates, pushing risks cold lapping, a hidden, unmelted gap against the sidewall. To avoid these defects, you have to map your technique to 3 constraints: the welding process, the material thickness, and your position. The first constraint is the most rigid. It depends entirely on whether your welding process produces a layer of molten slag. Pushing stick or flux cord wire drives molten slag ahead, burying it under liquid weld metal. This creates a hidden slag inclusion that fails inspection. Dragging prevents this. Pulling backward lets the arc strike clean metal, allowing slag to safely float on top. This is a non-negotiable rule for beginners and code welders alike. If there's slag, you drag. In clean processes like MIG and TIG, the choice between pushing and pulling is dictated by the heat you need to drive into the metal. When you push the torch, the arc points into cold base metal, while the liquid puddle rushes ahead, acting as a thermal cushion. This cushion makes the push technique ideal for thin sheet metal. It spreads the heat across a wider area, preventing you from burning through the workpiece. Pulling the torch reverses this dynamic. Without a leading puddle to absorb the energy, the arc strikes directly into the root of the joint. This concentrated arc force is necessary for root passes on structural plates over 8 millimeters. As this chart shows, while pushing gives you a wider bead, pulling is required to maximize penetration depth for deep structural fusion. In MIG and TIG, pushing prioritizes a safe, broad footprint, while pulling acts as a drill for structural depth. Your torch angle also determines how the shielding gas envelope protects the molten metal. Pushing the torch is superior for metals like aluminum and stainless steel. It floods the joint ahead of the arc with protective gas, cleaning the path and preventing oxidation before the metal melts. Then we have to account for gravity. In a vertical upweld, the fluid puddle is constantly trying to sag or fall out of the joint. Here, the push technique is preferred. The upward arc force supports the fluid puddle against gravity. Attempting a pull technique directs arc force downward, causing the puddle to bulge, sag, and eventually drip out. Because of these positional physics and gas requirements, you will often be forced to push the weld even on thicker materials. We can eliminate the guesswork with a logical framework. The first step is simple: determine your welding process. If the process produces slag, like stick or flux cord welding, the decision is already made. You must pull the torch to avoid inclusions. If you're using a clean, solid wire process, check your thickness. Heavy structural plates requiring deep root fusion resolve to the pull technique. For thin metal, oxidation-prone alloys like aluminum, or vertical up joints, the logic always resolves to push. Following this tree ensures you are working with the physical laws of thermodynamics and gravity. For apprentices, success depends on the slag rule. Dragging is how you produce clean, X-ray quality welds that pass inspection. For production fabricators, pushing provides the travel speed and flat bead profile needed for fast, cosmetically clean work that requires no grinding. But for structural and pipe welders, deep fusion is the priority. You must switch to pulling whenever the structural integrity of the root pass is the primary requirement. If you are working to a code, remember this equation. Changing your torch angle directly alters your total heat input. Because pulling digs deeper, it often requires slower travel speeds. This can inadvertently spike your heat input beyond what your qualified ASME procedure allows. Choosing between forehand and backhand techniques gives you total control over the thermal and structural reality of the welt.